All right. So here we are. Continuing on our workbook problems from section 4-3. We're going to look at part 2. Just a few questions to do today. They get a little bit more difficult at the very end. Number 21 brings into a few components that you have to take into account and is more like an old diploma exam kind of question. So we'll see that when we get there. But let's work up to it slowly. So we're going to be on the workbook pages 150 to 152, looking at questions 14 to 21. So looking at question number 14, it introduces the idea of something called a positron. And a positron is the antiparticle of an electron. So it's exactly the same mass of an electron. It has a charge of 1.6 times 10 to the minus 19 coulombs, like an electron, but an electron is a negative 1.6, and the positron is a positive 1.6. Has a second name, which is called a positive beta particle, and we'll see that when we get to nuclear decay. But a beam of these is traveling north at 4.0 times 10 to the 5 meters per second. So I did a quick sketch up for you. You've got the north, south, east, and west references on there. It tells us that that beta particle right here is indeed traveling upwards towards the north. I guess upwards is not a good word. They've identified the field as coming upwards. I prefer you to call that coming out of the page. And it's a positive particle. So remember, if it's a positive particle, you have to use your right hand. So when we do A over here, we're going to say, okay, our thumb of our right hand, because it's a positive particle, the thumb represents the velocity of the charge, the direction of the velocity of the charge. So that's going to be pointing, your right thumb pointing towards the top of your page, towards north. Your fingers, they represent the field. And the field in this case is coming out of the page. So I've got to spin around my back to the smartboard right now. My thumb is going upwards. My fingers are coming out of the smartboard. Now I look at my palm, it's coming towards me, coming towards the east. So your palm is the direction of the magnetic force. And in this case, that would be to the right-hand side of the page, or east. So the answer for A is east. So take a couple of seconds, get that all down, hit pause. We'll resume in a second. Okay, for question part B, magnitude of the magnetic force acting on the positron. So Fm is equal to QVB. That means that Fm is going to equal the 1.6 times 10 to the minus 19 times the velocity of that, which was given as 4.0 times 10 to the 5. Times the magnitude of the magnetic field, which they give us 30 milliteslas. So I'm going to put that as 30, leave it as 30, but I know that milli, or you can look on your formula sheet, means 1,000th of, or times 10 to the 3. So I'm going to pull up my calculator here. I'll walk through the keystrokes once. 1.6 second exponent minus 19 times the speed of 4 second exponent 5 times the magnetic field, which was 30 milliteslas, which is 30 times 10 to the minus 3 Tesla, to give us an answer of 1.92 times 10 to the negative 15 newtons. 2 sig digs, it's 1.9 times 10 to the minus 15. 1.9 times 10 minus 15 newtons. 15 newtons is our magnetic force in this question for B. Take some time to get that down. So for question number 15, magnetic force for a charged particle, QVB. But we want to solve this for the magnetic field strength, so it's going to be, we divide both sides by Q and V. Don't forget your master brackets around that Q and that V, or you may just have some issues. So the magnetic force was given as 2.56 times 10 to the minus 13 newtons. The charge, this being an alpha particle, remember, is 3.2 times 10 to the minus 19, but you can look that up on your data sheet if you're unsure. The speed was given here as 2.51 times 10 to the 7 meters per second. Okay, pulled up my calculator, 2.56 second exponent times 10 to the minus 13. Finished my top, I'm just going to hit divided by. Use some master brackets. 3.2 second exponent minus 19 times 2.51 second exponent 7, close your bracket, and hit your enter. If you didn't use those master brackets in your calculator, you will make an error. It'll take this top number, divide by the 3.2, and then multiply it all by the 2.51 times 10 to the 7. So you're going to be way off. So you saw the answer in the calculator was 0.0319, when it's rounded through significant digits. Tesla, fantastic. Take a little bit of time, hit pause. During a solar storm, the sun ejects millions of tons of charged particles such as protons and electrons at high speeds. The solar wind causes the Earth's magnetic field to fluctuate and induce currents in terrestrial conductors, transmission lines, pipelines, telephone lines in the old days. These geometrically induced currents, GIC, can damage conductors since they flow through. The Earth's magnetic field protects us against normal solar winds, but often insufficient during these solar storms. So we're going to deal with a proton. So if we were finding direction, we'd have to use our right hand. I don't think it's part of this question. Forms part of the solar wind traveling at 600 kilometers a second. We're going to change that to meters per second, don't forget. When it enters the Earth's magnetic field, which happens to be at that point 5.0 times 10 to the minus 5 Tesla. So again, it's not a very strong magnetic field around the Earth. Determine the magnitude of the maximum possible deflecting force experienced by the protons. So we're looking for FM. FM equals QVB. The charge of a proton, 1.6 times 10 to the minus 19 coulombs, times the speed. I like to just leave that as 600, so you're not messing with changing kilometers, 1,000 meters in a kilometer, so it's times 10 to the 3, so 600 times 10 to the 3, and that would have been meters per second. Times the 5 times 10 to the minus 5 Tesla. Let me get that a little bit neater for y'all. There, that's a little bit better. Let's pull up the calculator and punch that in. So we have the charge 1.6 second exponent minus 19 coulombs times the speed of these particles, which was given as 600 kilometers a second, which is times 10 to the 3 meters per second. Don't be confused with that being meters per second. So if you were, or kilometers an hour, if you were thinking that was kilometers an hour, you'd be dividing it by 3.6. This is kilometers per second. So we don't mess with the seconds, we just deal with the kilometers. That may be throwing some of you off. Times 5, second exponent, minus 5. That leaves us with 4.8 times 10 to the minus 18 newtons. So you may be thinking, that's not a very big force. 4.8 times 10 to the minus 18 newtons. These are protons we're talking about. The mass is very small. 1.67 times 10 to the minus 27 kilograms, so it doesn't take a lot of force to deflect them. Hit pause and copy that down. Question 17, you just have to fill in one word. When the velocity of the charged particle is parallel to the magnetic field, You remember we talked about yesterday, when it's parallel to the magnetic field, then the force is zero. It's only when it's, and again, not parallel, but we only deal when it's perpendicular. There is some force, and it goes away from parallel all the way up to perpendicular, but we don't deal with that in Physics 30. Question 18 is talking about a section of a mass spectrometer called the velocity selector, and we're going to get into that in tomorrow's or Thursday's video. I may give you kind of a half a day off tomorrow to just get caught up, work on your other classes. So Thursday we'll talk about a mass spectrometer and see all the different parts that go into a question that deals with that. So what it has is, you can see it has charge plates. So we have at the top negative plate, we have a positive plate. So what that means is these particles are going through and they're lithium ions, which means they're positive, which means the electric force is pulling them up. So the Fe is pulling them up. However, if you notice, we also have a magnetic field here. And that magnetic field is coming out of the page. Since these are positive, put your thumb towards the right-hand side of the page. Your fingers are coming out. That means your palm is facing downwards. So in other words, the Fm is pulling it downwards. This is similar to what J.J. Thomson did in his experiments, and you'll see that in Unit 4 when he determined the charge mass ratio of electrons. He used fields which were magnetic fields working against electric fields, and adjusted the strength of the electric field until the particles came straight through. So let's take a look at what these free body diagrams are going to look like. So for question A, we're looking at particle P. So here's particle P. It's going to come up. Obviously, the electric force is greater than the magnetic force. So we're going to have to draw the vector arrow from the free body diagram, from the object itself, larger for the Fe and smaller for the Fm. For B, when we're looking at the particle D is going straight through. What does that mean? That the electric force pulling it up is equal to the magnetic force pulling it down. So that's why it's able to go straight through without being deflected either up or down. So I drew those arrows the same, and I put a dash through either to show that they're equal. So in question number C, the particle Q is being forced downwards. That means the magnetic force is greater than the electric force, so our free body diagram shows a larger arrow for Fm. So something like that is what your diagram should look like for question number 18. You can hit pause and copy those down. So question number 19 has a few little tricks in it that you're going to have to just take your time and work your way through it. So question number 19. First of all, let's just go ahead and draw the free body diagram. That part's very straightforward. It says that it's going to be undeflected, which means that the magnetic force pulling it upwards is equal to the electric force pulling it downwards. That means the Fe going up is equal to the magnetic force going down. These two again are equal. So because it gets undeflected, one force was bigger, magnetic force was bigger, it would pull it down. Electric force was bigger, it would pull it up. So that's gets you that. So that free body diagram tells you that the Fe equals the Fm, or the fact that it's undeflected, it tells you the same point. So the electric force pulling it up is equal to the magnetic force pulling it downwards. So you remember from earlier in this unit, back when you still were here, we were studying electric fields. We said electric field, one of the formulas for electric fields was equal to the electric force divided by Q. So in other words, Fe is going to equal E times Q. So I'm going to take that up here and write in, instead of my Fe, I'm going to write in my EQ. And our formula from this unit, QVB. The first thing I realize I can do divide both sides by Q, and cancel out by Q. That means if I'm solving this for V, all I have to do is divide both sides by magnetic field intensity. So V is going to equal our E over RB. Magnetic field intensity was given us, electric field intensity was given us 500 newtons per coulomb, and the magnetic field 1.8 times 10 to the minus 3 Tesla. So let's punch this in the calculator. 500 divided by 1.8, second exponent, minus 3. Again, because I'm using my exponential notation, not my times 10 to the hat minus 3. If you use that other form of doing that, make sure you put master brackets. You don't need it if you're using this process. That gives us 2.78 times 10 to the 5 meters per second. So take a few seconds, hit pause, copy that down, and then we'll move on to the next question. So there's a few things implied in this question that you have to use your physics skills to analyze and figure out. First of all, it's singly charged. What does that mean? It has a charge of +1 or -1, which means its charge is going to have a value of 1.60 times 10 to the minus 19 coulombs. So if they said doubly charged, it'd be like an alpha particle, 3.2 times 10 to the minus 19. So that's the first thing that you have to infer from it. The second is that they tell you, again, that we're thinking about it being in a circle. And sometimes they're not going to say the word circle, they're just going to give its radius of curvature. Remember that when a charged particle from yesterday enters a magnetic field, it goes into a circular trajectory. When it goes into an electric field, it's going to go into a parabolic trajectory. So remember, this is a circle. Because that's true, the magnetic force that's being applied to it is equal to the centripetal force of the Fc. So anytime it's going in circular motion, because of a magnetic field, we can assume that Fm equals Fc. When are you going to know you have to use that? Again, your keys are, it's going to say circle, it's going to say radius. So the formula that's not on your formula sheet, one that you're expected to remember or to derive each time, is that Fc is equal to mv squared over r. Fortunately, we don't have a diploma exam, so certainly write that on your formula sheet. If I present you with one for our final, I'm going to add that in just like the good old days. So I'm going to transfer that over here and make it mv squared over r. Now in this particular question, we're looking for the mass. So we're going to have to get rid of everything else. But our first move is to simplify this a little bit. We have a v on this side, we have a v squared on that side, so I'm going to cancel that out with my square. So now I have to get rid of the r, so I multiply both sides by r, or simplistically, it's on the bottom, goes to the top. I have to get rid of my v, it goes to the bottom. So ultimately, my mass is going to be equal to my q and b, which are on the top. But I brought my r up, I multiplied by r, and all that's over my v. So my q is 1.6 times 10 to the minus 19 coulombs. Again, it wasn't explicitly said to us, but they just told us that it was singly charged. The magnetic field intensity, B, was given as 410, decimal 0.410. Nicely, good old buddies, Kennedy Oswald gave us our radius in meters, not given us to us in centimeters for another thing to mix up, 0.680 meters, and this was traveling at a speed of 8.10 times 10 to the 5 meters per second. When I put that in my calculator, filled it out, I got 5.51 times 10 to the minus 26 kilograms. Hit pause, take a few minutes, copy that down, double check my calculations, Mr. Oswald as well, and make sure that we did them correct. Question 21, again, is going to pull together that. This is going to go into a circular rotation. The cue for that is they gave us the radius. Be careful, the radius here was given in centimeters, so we're going to have to convert that to meters. So Fm is equal to the Fc. The magnetic force causes the circular motion. That's why those are equal. It is the Fm which is causing all of the Fc. So the first thing I'll do, cancel out my V. I'm looking for this V, so the R goes up and the M goes down. Ultimately speaking then, Q, B, R over the mass. So we start off with our charge. Go back to the question. Pay attention to what you're dealing with. It's an alpha particle, so the charge is going to be 3.2 times 10 to the minus 19 coulombs. And I'm going to put the mass in now so I don't forget what I'm dealing with. 6.65 times 10 to the minus 27 kilograms. Again, if you're not sure of those, check your data sheet if you're not 100% sure when you're doing questions. Times our magnetic field intensity, which is 1.20 Tesla. So when it comes to the radius, I'm going to just leave it as 2.34, but it's in centimeters, and a centa is 100th of, or check your sheets, times 10 to the minus 2 meters. Punching that into my calculator, I get final answer of 1.35 times 10 to the 6 meters per second, which is a very fine number indeed. Okay, folks, I'll post this up to YouTube, and I will go ahead and produce a quick bell work to go with it, and try and get those done by Thursday. So work on them today, work on them tomorrow. I'm going to be assigning it through the Google Classroom. So if you haven't signed up for that yet, make sure you do. Accept the invitation. Everything will be located there. There'll be a direct link to this video. Well, you know that if you're reading this. I guess I shouldn't even bother me saying it. Okay, have a good one.